In some cases, we need to do the opposite of what we've been doing so far, meaning that, in the previous slides, what we were doing is that we were finding z, and then we find the probability of z being less or equal than that specific value. Sometimes we are given the probability and we want to find the value of z. Okay, so this is what we mean by here. We want to find z given the probability. Okay, so the area is given for us. To do that, or before I show you how to do this, let me introduce a notation that is standard, and it's standard across different topics. So I want to let me explain it for you. We denote by ZA. What's ZA? It's the value of z such that the area on the right hand side is equal to a. Okay, right hand side. What we were mainly working with for any value of z with the area on the left hand side. Now we are using a notation where we use a subscript of a to represent the area on the right hand side. Why this? Because this is common, and we need to learn about that. So in other words, p of z greater than za is a. Okay, so let's see. Let's see that on the curve. So these are the curves. This is the curve that we were using. This is z table where we were focusing on a value z star, a critical value z star, such that the probability of z less or equal than z star is a star. Okay, but since now we want to denote the z in such a manner that the area on the right hand side is something, so I want to concentrate on the area on the right hand side of that z. Okay, so this is the area that I'm interested in. And by the way, this a and this a star, they are related. How? The sum of these two areas is equal to 1. Why this? Because these two areas represent the total area under the curve, and we know that the total area under the curve is equal to 1. So if I know this a star, I will be able to tell what's a. If I know a, I will be able to tell what's a star, and we're going to use that a lot. Okay, so this z star is now have a special notation. What is it? This is our ZA. Why? Because the probability that Z is greater than ZA, right? It's that area, it's equal to A. So that's why we are calling it ZA. So let's apply what we just learned in this simple example. So we want to find the value of Z such that the probability that the random variable z is greater than it, so then that critical value is 5%. Okay, and we learned that we will denote that by z 0.05 because the area on the right hand side is 5% or 0.05. Okay, so let's see that on the curve. Okay, we are interested in the area of 5%. So we will call that z as 0.05. Okay, so what we can write about that z, we can write that as defined. Okay, p of z greater than z 0.05 is 5%. Okay, which is 0.05. So I want to find the value of z. And usually we go to the z table, right? However, in the z table, the area corresponds, or the areas that we read correspond to p of z less or equal than z star. Okay, so in order for me to find any specific z, I need to define what's the area on its left-hand side, right? P of z less or equal. But this is easy. If I know that this is 5%, so what's remaining for me? It's 95%, right? As I said before, the area under the curve is 1. So if this area A is 5%, that means all the remaining area is 95%. And the remaining area is what? This is P of Z less or equal than this value that I'm interested in, okay, which is equal to 0.95. Now I can use the Z table, right? So I will go for the Z table, and I need to locate an area equal to 0.95. Now, in many cases, you will not be able to read exactly the same, the value of the area that you're looking for. Look, here I can see 0.9495, very close to 0.95, and this is 0.9505, also very close. And in fact, both of them are equally distant from the value that I'm interested in, 0.95. Which means what? If that was my area, 0.9495, then my Z would be what? It would be 1.6, 1.64, and the other one is 1.65. So if I'm looking at an area exactly between these two, okay, which is here, then my Z value is the average of 1.64 and 1.65. So it will be 1.645. Okay? This is how we get Z given a certain area for us. This example is important because it emphasizes a very important characteristics of the Z table or any, of the Z curve or any PDF of a normal distribution, which is the symmetry around the mean. Okay, let me illustrate what I'm saying here. In this question, you see, the title is find minus Z 0.05. And what's Z 0.05 itself? It's the Z value such that the area on the right hand side is 0.05, which means if I want to find minus Z 0.05, this is a Z value such that the area on the left hand side is 5%. Look what I mean by this. Okay, this is what we did in the previous example, where we located in the z-axis a z 0.05 such that the area on the right-hand side is 5%, right? Because we're using the ZA notation. So what's minus z 0.05? The curve is symmetrical with respect to the mean, okay, which is the mean is 0, which means if this is the distance between the mean and this value, if I go at the same distance, okay, I will read a value, okay, which is equal to minus z 0.05 minus that value, and I know that this area will be equal to that area because of the symmetry. And now it's easy, right? Because what's that area? This area is P of Z less or equal than minus Z 0.05. So now I can look directly at the table. I don't need to find another area and then look at the table. This area is P of Z less or equal than a specific Z value. So I go to the table and I want to locate 5% or 0.05. As we did in the previous one, now we can see that we have two values are close to what I want. This one and that one, and in fact they are equidistant. So for this one correspond to Z minus 1.64, okay, and the other one is minus 1.65. Also I'm looking for the one in the middle, so which means my Z will be between minus 1.64 and minus 1.65, so I take their average and Z is minus 1.645. So I hope that you understand the importance of the symmetry of the Z curve. A final note about our notations, our new notation ZA. Why it's important? Because it relates to a concept that, or to a metric that we have used before, right? It's a measure of relative standing, which is the percentile. Okay, remember what's a percentile? For example, 95 percentile, 80th percentile. It's the value in your data sets that has, for example, if it's 80th percentile, 80% of your values are below that. Okay, so we can use then our notation, this ZA, to represent a percentile, right? For example, when we say Z 0.05, meaning that the area on the right-hand side is 5%, meaning that the area on the left-hand side is 95%. So which means that Z 0.05, which is 1.645, is our 95th percentile. Okay, this is important to note because it really relates to a very important measure of relative standing. And that will be it for our discussions about Z value.